So now we are going to start our discussion of inviscid flows. We'll discuss them some more in the second quarter, in particular when we discuss ideal flows, and we will discuss them in more details then, but we're going to start with a first look into inviscid flows. And the first thing we're going to do is to start from our now familiar Navier-Stokes equation, and we are going to non-dimensionalize to discuss, to show how these equations become reduced to the Euler's equation when when the effect of viscosity are negligible. So here we'll start with the non-dimensionalization of the Navier-Stokes equation. Alright, so before we non-dimensionalize the Navier-Stokes equation, let's think about our regular, standard problem in fluid dynamics. We have an external flow around an airfoil. If we're thinking about the relevant physical parameters, here we have, for instance, a velocity at infinity. We have a characteristic length scale, L, that could be the length scale of the chord length of our airfoil. We have the material properties of the fluid, that would be the density, and the dynamic viscosity. We could have, if that was an airplane, effects of gravities. Sometimes they are not important, sometimes they are. We could have the effect of gravity, and then if we're interested, and then it really depends on the problem, but it could be that, for instance, we are interested in the wake. All right, and something else that we could have is we could have another time scale. And that could be, for instance, if we were interested in the flow in the wake of this aircraft, of this airfoil, where you could have shedding, and this shedding happens at a certain period, and so that would give you an additional time scale. In some problems, you could have, for instance, the problem of fluttering, when this airfoil oscillates up and down, and the period of that oscillation, tau, would give you another time scale. What you could have alternatively also is that the flow is unsteady. Let's say this airfoil is in the wake of another airfoil, and then you would have an incoming flow here with vortices, periodic shedding, and there that would give you another time scale. So there could be another time scale. I'm going to call it tau. This is in our particular example. In many examples that you will see, there will not be such a time scale associated with unsteadiness, but for now, we'll assume that we could have a For example, one such phenomenon could be vortex shedding. Okay, and so now if you think about our Navier-Stokes equation, in our Navier-Stokes equation we have certain properties, material properties, rho, mu, and g. They come into our Navier-Stokes equation. They are just properties. They're always there, and they will be fixed by the problem. So these are already, they're already fixed by the problem. And again, given a certain problem, then your boundary conditions or the dimensions will give you scales for the other terms in the Navier-Stokes equation. So the velocity field, for instance, at some point the velocity is small, in other points it could be larger, but you have a typical scale here in that problem for the velocity, and that would be the velocity u at infinity. So when you start non-dimensionalizing, then you will write everything. So if you're thinking about your velocity vector, u, right, this is a function of position and time, and you non-dimensionalize it by simply writing u as the product of a vector field, which is now non-dimensional, So this tilde here indicates that that the quantity is non-dimensional, times, of course, our velocity scale. Okay, so note here, this has the right dimension. This is meters per second. This has no dimension, and this is our scale of velocity, which is in meters per second. Okay, but there are other quantities which we have to non-dimensionalize inside of a Navier-Stokes equation. The first one is everything which has to do with position, so x here. We have to non-dimensionalize x, and again we're going to write it as, this is a position vector, as a non-dimensional position vector times our characteristic length scale. And we can do the same with time. Time would be equal to non-dimensional time times our characteristic time scale. And then the last quantity which we have in the Navier-Stokes equation is the pressure, right? And here, if you think about pressure, there are several ways you could non-dimensionalize the pressure, and that simply comes from the fact that both rho and mu have kilograms, and you could use both a scale for pressure that uses rho or a scale for pressure that uses mu. The best at this point for pressure, I think, is always to not yet really explicitly write in terms of u, rho, nu, and all of the different constants in L, what the scale for pressure is. And that is because pressure is really the stress, we discussed that, it's the stress inside of a fluid, inside of a flow, which will develop to oppose the change of volume of a material element. Right? And therefore, pressure really reacts to the dominant forces. So if you have a force which is driven by inertia, pressure will be reacting to inertia. If you have a flow which is dominated by viscosity, it could be that really what causes the pressure is a response to the viscosity which is trying to change the volume of a material element. Note here that for our position vector, I explicitly assume that L is a relevant length scale in both x, y, and z direction. But that is not always the case. In the second quarter, we'll discuss lubrication theory, where in one direction we have one length scale, and in the other direction we have another length scale. But for now, we can assume that we have the same length scale in all directions. And then note that what we also have are differential operators. And therefore, our differential operators we need to non-dimensionalize as well. Right, so this nabla is really a partial x, partial y, partial z. We have x, y, and z here. So when we write it, we will write it as equal to 1 divided by L times a non-dimensional nabla. And then again, this has units of 1 divided by a length scale, so meters minus 1, and that has the same dimension as this. This non-dimensional nabla has no dimension, and here we have really meters minus 1. Okay, and so with all of that, we can directly non-dimensionalize our Navier-Stokes equation. So recall our Navier-Stokes equation. And so what we're going to do is to simply replace all of our fields and all of the notations by our non-dimensional notations. So for the first term, we have rho, and here u is a u times a non-dimensional u, partial tau times a non-dimensional t. And we can do this for all of our different terms. So u here is again our characteristic length scale for u times non-dimensional u dot nabla. So we'll use our 1 divided by L times the non-dimensional nabla operator. And we have a u left here. So this is again characteristic length velocity u times non-dimensional u. And we do this for all of our terms. So the pressure term becomes our scale for pressure divided by L times the non-dimensional nabla times our non-dimensional pressure field. Our viscous term becomes mu characteristic length scale u divided by L squared times our non-dimensional Laplacian of u minus rho g z. So I can rewrite all of the different terms. So note here that when we write our equation this way, each of these terms here, every single one of these terms, still has the units of newtons per meter cubed, right? So therefore of kilograms, meters minus 2, second minus 2. So if you look at each of these terms and you take the units, you'll see that each of these are newtons per meters cubed. And so when we non-dimensionalize these equations, then we just have to divide all of these by a group which has certain dimensions. And the way we'll do that really depends on which regime we're looking at. So let's look first at the inertial regime. So in the inertial regime, we'll assume that the pressure reacts to inertial forces. And so what sets the scale for the pressure is an inertial force. And remember, if you think about the stagnation pressure, it gives us 1/2 of rho u squared, then you'll find the scale for pressure, and we'll scale the pressure with rho u squared. So here, that means that we, instead of putting pi, we put rho u squared as our characteristic scale for pressure. And so what we do then is that we take this equation, let's call this equation 1, and we will take equation 1 and divide it by a characteristic scale here for a force per meters cubed, so per volume, and that force will be, you'll see it here, rho u squared divided by L. And so we divide every single term by rho u squared divided by L. Note that in front of this term you will have nothing left. In front of that term you will have nothing left. When you divide rho u divided by tau by rho u squared divided by L, you will be left with L divided by u tau partial u partial t. And note, of course, now that this group now really is non-dimensional. So this whole thing here is non-dimensional. This is meters per second times second. So this is meters, and we have meters divided by meters. This is indeed non-dimensional. Plus u grad u minus the gradient of pressure. And here, when we divide mu u divided by L squared by rho u squared divided by L, we're left with another group here, which is also non-dimensional, right? So if you look at the dimension of this, you realize this is non-dimensional, times the Laplacian of u, minus our last non-dimensional group now, which will be GL divided by u squared, and z is a unit vector. Okay, so this is here our Navier-Stokes equation written in non-dimensional form. And when we write it this way, you see that we have three non-dimensional numbers that appear. So this is the last way that we discussed dimensional analysis, we discussed scaling analysis. Once you start solving the equations, when you non-dimensionalize the relevant equations which govern your system, then you have the relevant non-dimensional numbers which appear. And so you have this number here, that number here, and this one there. The first number, which is in front of the unsteady term, is called the Struhl number. Usually it is written as an ST, and this is equal to L divided by, so your characteristic length scale divided by your characteristic velocity times your characteristic time scale. If your time scale is given as a frequency, so time scale is 1 divided by frequency, then you can write your Struhl number as L times F times U. It really depends what is given to you. So when you write it this way, this is one way of interpreting the Struhl number is as a non-dimensional frequency characterizing the unsteadiness inside of your system, your fluidic system. And so if you want to interpret the Struhl number, you can see it as a ratio of two forces, as a ratio here of the unsteady inertial force divided by the steady inertial force. Indeed, note that we obtained this scale here when we took our scale for the unsteady force and derived it by our scale for the steady inertial. So when we took our scale for the unsteady inertial force and divided it by our scale for the steady inertial force. Our second non-dimensional number here is 1 over the Reynolds number. So it's the inverse of the Reynolds number. We define the Reynolds number as the following number: the density times the characteristic velocity scale times the characteristic length scale divided by mu. And one way you can understand the Reynolds number is to think of it as a ratio of two forces, the ratio of the inertial forces divided by the viscous forces, such that when the Reynolds number is much larger than 1, the inertial force dominate. So think that Reynolds number much larger than 1 means that inertia dominates, and when the Reynolds number is really, really small, right, when this term here, when the denominator is really large, then the viscous force dominate. Finally, the last number here is related to the ratio between gravity forces and inertial forces, and usually in the literature this is represented as will be the square of a non-dimensional number, which is called the Froude number. And so we'll take the Froude number as the square root of the inverse of this number here, so we'll take it as u divided by the square root of gl. And so it represents the square root of the ratio between inertia forces to gravity forces. So with that, I can rewrite the non-dimensional form of the Navier-Stokes equation as the Struhl number times the unsteady term plus the nonlinear inertial term minus our gradient of the pressure term plus 1 divided by the Reynolds number of our viscous term minus 1 divided by the Froude number squared on our unit vector z. And so note that when the Reynolds number is really large, when inertial forces are much larger than viscous forces, 1 over the Reynolds number becomes a really small number, and therefore this term becomes very small because it's multiplied by a very small constant. And so in the limit where we can neglect, where the viscous forces are negligible, then we can omit this term, which yields the Euler equation. And so the Navier-Stokes equation then simply becomes, so we have our inertial term on the left-hand side, the unsteady inertial term, and the nonlinear inertial term, the pressure term. This term becomes equal to 0 minus our body forces. This here is if we write the equations in non-dimensional form, and if we write it in dimensional form, when we neglect the effect of viscosity, the Navier-Stokes equation reduced to what are called the Euler equation, which are just the same, but without the same as the Navier-Stokes equation, so the continuity equation and the momentum equation, but without the viscous term.